All right, so we've had a little bit of experience and discussion about spectroscopy, but we're going to go through this and look at the highlights of the chapter and make sure that there's nothing that we're missing, okay? So spectroscopy is studying the way that matter interacts with electromagnetic energy or electromagnetic radiation. All right. Now, electromagnetic radiation essentially is what we describe as an electrical field oscillating with a magnetic field. And these wavelengths of energy we call electromagnetic energy. And light is the visible region of this electromagnetic energy. All right. Down here, there's a nice spectra showing the different wavelengths. So here in meters, right, 10 to the minus 8 or 10 to the 8th positive 8, right? So very long wavelengths in meters of electromagnetic energy. Radio waves, AM, FM radio, microwaves, IR, and then we have our visible region, which spans between 400 and 700 nanometers. We talked about that already. That's something you always want to know. UV is the region here, right? Below 400 down to about maybe 120, something like that. And then you get smaller, you get into X-rays and then gamma rays. Now tell me, Fred, what side is more energetic? Gamma rays or radio waves?
More energy?
Yeah.
X-rays and gamma rays.
That's right. You know, if you stand in front of the X-ray machine without any protection for too long, it'll cause cancer, right? So even the UV rays from the sun are enough energy to break carbon-carbon bonds in our DNA, which sometimes lead to mutations that don't get repaired properly, which can lead to skin cancer, right? So more energy down here. We haven't found any ill effects of IR, microwave, longer radio waves on humans, on tissue, on cellular life. So you see lots of experiments done with this. You see lots of people concerned about the result of holding a cell phone to your ear. There hasn't been a whole lot of evidence that any of these cause problems. Okay? You know, people could say, oh, you never know, you never know. Well, we kind of know. We know because the energy associated with UV rays is the amount of energy that's in a carbon-carbon bond, for example. These types of energies are less than the energy which is in a typical bond. Therefore, these types of energies are non-destructive to chemical bonds. They will cause movement, but you won't cause destruction. Okay, so that doesn't mean you can't heat things up. I mean, we know that microwaves do heat things up, right? You can heat up water molecules. But all right, so let's look at some common relationships that we probably or should have gathered in Chem 105, and the relationship between the wavelength, the speed of light, and the frequency. Do you remember this?
Yeah, the longer the wavelength, the shorter the frequency.
That's right. Very good. And frequency is what is related to our energy, right? Using Planck's constant here as a constant that will give us the correct units in joules as opposed to cycle or per second. That's what Hertz is. And we can find out the relationship between energy and wavelength, right? Inversely proportional. And that's what we're seeing here. Longer the wavelength, lower the energy. Okay, so those are some relationships that we probably already knew and should remember. Here are different kinds of spectroscopic techniques that utilize these different wavelength ranges. Okay? X-ray, gamma rays, very high energy, right? UV vis, UV, relatively high energy. You still have to be careful when you're using it. Visible region, that's relatively low energy. Microwaves, radio waves, all right? Have you heard of NMR, nuclear magnetic resonance?
No, I don't think I have.
Well, it's a topic in organic chemistry, where you can use how radio waves interact with organic molecules and learn about the structure of the organic molecules.
Oh, I think I know what that is. Yeah, I've heard about that.
Okay, good. So nuclear magnetic resonance is a form of spectroscopy that utilizes radio waves. All right. So when you're looking at energy being absorbed, right, we're watching the impact of our photon of energy, whatever wavelength we're shining on our material, right, impacting with our material. And we say that the electrons in the molecule or in a system are at their ground state. And when that wavelength of light corresponds to the energy, that the frequency of your wave or your bond, right? Bonds are like stretching springs, and depending on the distance of the atoms, the nuclei from each other, and depending on the size of the nuclei, determines what frequency that bond can stretch at. So not all material can absorb all electromagnetic forms of electromagnetic energy, all wavelengths, because again, it's specific to the energy that is in their bonds. But if the appropriate wavelength of electromagnetic energy, appropriate energy comes and hits a bond that can absorb it, then those bonds or that orbital will be excited, and we call that absorption. And then as the energy is released, it can either be released in the form of heat, so the movement slows down and the air molecules around it or the system around it absorbs that movement, or you can get the re-emission of a different wavelength of energy. All right, so fluorescence is an example of when you don't measure how much energy was absorbed, but you measure how much energy is re-emitted, or that fluoresces off of the system as the electrons settle down to the ground state. Okay. All right, let's see. I think there was one other thing that we wanted to look at up here. Maybe not. No. Okay. So you get a typical absorption spectra like this, right? This is for a chemical dye, and you get a wavelength of absorption, right? Now, do you remember the colors for 400 to 700 nanometers?
Let's see. 400 is the highest energy of the visible range, and so that's the closest to UV. So 400 must be violet or purple.
That's right, very good. And so 700 is the what?
The red.
Very good. So we're looking at red, orange, yellow, green, blue, purple as we move this direction, right? So we have this here absorbing. Does that mean that this material, this dye, is going to be that color?
I can't remember.
If this is the light wavelength that's being removed from the spectra by our sample of anthracene dyes, then we're not going to see that color. What we're likely to see is the kind of the rest of the colors that aren't absorbed. So what would you say we would see?
Oh, this would be red.
That's right. And it says down here that this is what we see in cranberry juice, the anthocyanin dyes. Okay. Here is a different example of emission intensity. Now here, again, we're not looking at the light that was absorbed, but we are using photoluminescence. We're looking to see the wavelengths of light that are emitted by the molecule after it absorbed some energy from somewhere else. Now, if a molecule or a system can absorb energy, and then re-emits it it's always going to be re-emitted at a different wavelength, and it's always going to be a lower energy. The photon of energy that's released is going to be lower than that of the energy that it absorbed. It can't release more energy than what was absorbed, and it can't release the same amount because a certain amount of it went into the molecular motion. Okay, so this re-emission, if the re-emission is at 500 nanometer, the absorption had to occur probably around 300 nanometers because that's a higher in energy wavelength. Does that make sense?
Yeah, that makes sense, I think.
Okay, good. So we also have some examples of technique that don't involve the exchange of energy between a photon and the sample, but are very important techniques nonetheless. X-ray diffraction, right? Very important technique in which the X-rays are diffracted by the waves, the other waves around the molecules, which are electrons, right? Electrons behave like waves, and when two waves come together, you'll get some light. You'll get light doing some performing, following light properties, and one of those is diffraction, right? Okay. So here is an example of very tight bands of emission spectroscopy. So here, the band width right here is shown between 500 some nanometers, 525, all the way down up to 600 nanometers, and so a wide bandwidth occurs. Here we have a very narrow bandwidth, and it's better when our bandwidths are narrow, because if you had a very wide bandwidth and there was another chemical that was absorbing in there, like this looks like it's almost two chemicals there. Can you see that?
Oh yeah, two species that are absorbing or emitting.
Yeah, that's right. Two species there. So it's a very wide emission range. Well, in spectroscopy, you want to have very narrow bandwidths so you can distinguish all the signals that you have there. Okay? So to get certain wavelengths of light, we have different sources of energy. A hydrogen lamp or a deuterium lamp. Now, you've heard of a neon light, right?
Yeah, I told you I went to Vegas.
That's right. You have neon lights, not just in Vegas, all over, right, Fred?
Yeah, okay.
But inside the tube of a neon light is neon gas, and we are applying a potential across that gas, and as the electrons pass through that system, electrons are excited on neon and then relax back down, and energy is emitted. Okay? So you can do that with hydrogen gas. You can have a hydrogen lamp or deuterium. Deuterium is a hydrogen atom with one extra neutron. All right, that's what deuterium is. And those lamps produce a good range for us in terms of ultraviolet light. Now, unfortunately, these lamps often don't last very long. They burn out relatively easy. But often this is a wavelength of electromagnetic energy that it's hard to get. So you'll see frequently deuterium lamps being used. Tungsten lamps give us a nice, encompass the visible range very well. A xenon arc lamp doesn't give as low of a UV range in the UV range. However, it's good because these xenon arc lamps, they last for a very long time, and they can give a source that's very wide in terms of right along the visible and ultraviolet range, and all the way up into the near IR. Okay, so different sources of our electromagnetic energy. So notice that if you look at two samples, depending on how you look at them, the depth of color will be slightly different. If you look at the side of a tube like this, as opposed to looking down it like this, the path length, the amount of light that's being absorbed, is different. Do you see that?
Yeah, the path length. We talked about that. Path length's in Beer's law.
Very good. Path length is a component in Beer's law. All right. So a diffraction grading, we talked about that as well. And what diffraction grading does is allows us to take a light source, put it into one column, and then diffract it with some sort of a prism here. And once it's diffracted, then all the wavelengths will spread out. Have you ever seen a prism held up to the sunlight or up to a light, and you get a rainbow on the wall?
Yeah, I've seen that.
And you can see that in rainbows as well, when the water acts as a prism and diffracts the light from the sun, right?
Yeah, okay.
Well, you can use this, and then you can choose exactly what wavelength you want to pass through your excitation slit, or pass through your slit that's going to head to the sample, right? And eventually to the detector. So the diffraction grading allows this to occur. And you can then slightly bend this mirror, or bend the diffraction grading, or move this back and forth, and select the specific wavelength that you're interested in providing to your sample. Monochromatic source, meaning we're going to have a short wavelength range, or a single wavelength. Polychromatic source of radiation, right? Lots of wavelength can be absorbed at one in one sample. Okay. All right. Here's an example of what we call a photomultiplier tube. A photomultiplier tube takes the light that comes through your sample, and as it reflects off of certain material, it will the photoelectric effect will cause more electrons to be emitted. And then this is repeated with another material that will produce the photoelectric effect. And then we have mirrors that will allow this to bounce around. And in the end, you have a significantly increased amount of electrons which are jumping to your source from just a small amount of light. So a photomultiplier tube like this will allow very small signals to be measured in the terms of current here, right? So very good. All right, so let's look at absorption spectra. Now, absorption spectra, sorry, in the absorption spectra, yeah, absorption, looking at absorption. Absorption is not just UV and visible light. It can be infrared, right? And it can be, there's any wavelength region that you want to look at. As long as the molecule or the system will absorb it, you can use that wavelength. This example here is showing, again, our transitions from our ground state and what we call them our molecular orbitals, all right? So in Chem 105, we talk a lot about atomic orbitals, and then we talked about atoms coming together to form hybrid orbitals. And hybrid orbitals can kind of combine, or you can think of them as functioning on a molecular level. We didn't talk a lot about molecular orbitals, but molecular orbitals, we don't have to understand them a whole lot, but just know that there are, just like atomic orbitals, you can excite the electrons from your molecular orbital to a higher molecular orbital. Okay? And this transition, the energy of the transition can be described as the vibrational quantum number, all right, which is just going to be, some value 0, 1, 2, some integer, plus 1/2 Planck's constant times the initial fundamental vibrational frequency. So here's our fundamental vibrational frequency, and the energy to transition between this frequency and your vibrational quantum number that you want to transition to gives us, it can be calculated this way, right? And basically the idea here is we are monitoring absorption, and when we monitor absorption, we're monitoring transition of molecular orbitals. And so when you see something like this, that means that there are, in that range of energy, right, the molecule has bonds that can respond to that wavelength, those energies, right? We saw before, let me, instead of going back, let's just show this really quick. We saw in the previous section how we can plot absorbance versus wavelength. And let's say we went from 400 to 700 nanometers, and we would see something like that, right? And we would know that these are the regions of light where things were absorbed, and this is in nanometers. Well, there's another way of expressing, which is a popular way of expressing energy, not in the form of nanometers, but what we call wave numbers. Now, wave numbers are just 1 over the wavelength of the electromagnetic energy in centimeters. So if you take your numbers in nanometers, convert them to centimeters, and do 1 over that value, this is what we call wave numbers. So now when we go 1 over the value, if you take 1 over 4,000, that's going to be a higher energy than 1 over 1,000 in terms of wavelength. So let's do some math on that. 200 nanometers we know is higher in energy than 700 nanometers. All right. Actually, yeah, that's good. So 200 nanometers, that's 0.2 micrometers, or 0.0002 centimeters. Let's see, micrometers. No, that would be that many millimeters. So we have one more zero in here for centimeters. Okay, so 700 nanometers, 0.2 micrometers, and then 0.000 millimeters, 0.002 there we go, millimeters. And then we got to go back the other way, 0.002 centimeters. So this is, 0.007. There we go. Made a mess of that. And this is not going back that way, it's 0.002 centimeters. So this is 0.002 centimeters, and this is 0.007 centimeters, okay? Now, if I take 1 over my 0.002, I get a wave number of 5,000. Or sorry, 500, wave number of 500. So this is 500 wave numbers, which is in units of centimeters to the -1. All right, 0.007. Uh, 142 wave numbers in the units of centimeters to -1. So what's higher in energy?
500 wave numbers is higher in energy.
Very good. So in terms of wavelength, a longer wavelength is lower in energy, but in terms of wave numbers, a higher wave number is higher in energy. Got that?
Yeah, so why do they do that?
I think it's mostly tradition. Yeah, I think that's the best way to kind of simply state that. But IR spectra are almost exclusively expressed in terms of wave numbers. Okay? All right. So And also, you want to pay attention to your y-axis here, because this is in terms of percent transmission, right? Percent transmission. Now, transmittance. We talked about the relationship between transmittance and absorption a while back. Do you remember that?
I'm not sure that I do remember that.
Well, here we have our official, if we get way down here, we have our official explanation of our relationship between transmittance and absorbance. Okay, so here, if I have a light source that's trying to travel through a sample, PO representing the intensity of the light coming in, PT here representing the intensity of the light that made it through the sample, the blank, right, the amount of light here that comes in, PO should be the amount of light that comes through the blank. All right, so that's, we blank it that way. And then transmittance is this ratio of the light that got through over the light that was that got through a blank. Okay, and that transmittance can be expressed in terms of a percentage, because this is always going to be a fraction that's 1 or smaller, right? And then you can also take the negative log of that fraction, that's between 1 and smaller, and the negative log of that fraction will equal absorbance. And because PT over PO, the units of intensity here are dropped out, that's why we say that absorbance is a unitless value. Okay, very good. Now, one thing that I always want my students to remember is what percentage of light is absorbed if your absorbance value is 1. What percentage of light is absorbed if your absorbance value is 1? Now, we talked about that a while back. Do you remember?
I think I do remember. Let's see. If that ratio, PT to P0 there, if that ratio was 10 on top and 100 on the bottom, so like 10% got through out of the 100 that was going to get through.
That's very good.
10 over 100, that would be 0.1.
Very good.
And then if you take 0.1...
Okay, I'm going to do this for you in your calculator, right?
Yeah, 0.1. Take the negative log of that value.
Yeah.
That's 1. So absorbance of 1 means that you took the negative log of 0.1. And to take the negative log of 0.1 means that PT was 10 and PO was 100. So 10 got through and 90 out of the 100 was absorbed. So if you have an absorbance of 1, 90% of your light was absorbed.
Very good. 90% of the light was absorbed. All right, and that's why we want to keep that from getting towards too close to the 100% of light being absorbed, to be kind of in more of the stronger signal region. We generally would like to avoid absorbance values higher than 1. Okay, very good. Now, Beer's law, here's Beer's law right here, right? Absorbance equals concentration, and that's usually where we spend most of our effort. But now we want to become familiar with what's called the absorptivity, or the extinction coefficient, or the molar absorptivity, all right? And this extinction coefficient, molar absorptivity, right? What are its units? What do you think its units are?
I thought absorption was unitless.
Absorption is unitless, that's right. But concentration is surely not unitless, is it?
Oh, concentration. No, concentration should be like molarity or something.
That's right. So if we say molarity for the concentration, and if we want to, here's a good little setup here. Absorption, unitless. Concentration, molarity. Path length, it can be any units of meters, but generally it's centimeters, and more often than not, the equipment is such that you can keep it to 1 centimeter. Then we can see that the extinction coefficient is going to have units of how much light is absorbed per centimeter per molar of solution. You see that?
What does that mean?
Well, the extinction coefficient then essentially is saying how much light a 1 centimeter sample would absorb if its concentration were 1 molar. Now, you're not going to see a 1 molar solution ever placed into a spectrophotometer because that's a very high concentration, and Beer's law only works with dilute concentrations. Now, it could be that the extinction coefficient is really low, and therefore you do need a high concentration like that. But if you don't have a good absorbance of light, then you don't want to use spectroscopy. You want to use some other technique to measure the concentration of it, right? So in general, extinction coefficients are relatively large, in the hundreds or thousands or tens of thousands or even hundreds of thousands. And again, it's how much absorption you would expect to have if you had a 1 centimeter path length and your concentration of your sample was 1 molar. Okay, very good. So I think that that's all we want to get out of this here. We can look at, we talked about this already, but we can look at another example. If I have an absorption spectra like this, and I plot absorbance at this wavelength versus concentration, right? As I change the concentration, this wavelength, if I decrease it, the absorbance at that wavelength, my lambda max, decreases. And you can see this plot is linear as it decreases because it's going to respond linearly to the concentration. However, if I plot off of the peak here, I can get a linear relationship, but it loses its linearity at these higher concentrations because there's not as much upward motion. If this is where we're going upward, this will rise initially, but then as this rises a linear amount, this one is not going to respond linearly. Okay, so this again is an example of why we want to do what?
To measure at the lambda max.
That's right, be at the peak. If we're off the peak a little bit, things are okay. We can even be off, way off, and still have a very large linear region, but it's better to be at the peak. Now, sometimes you'll get two substances in which the absorbance of the two substances in solution, right? So this solution substance in solution A absorbs there, and some solution in B absorbs there, right? And so we get, if you were to look at these in the same container, it would look something like this, right? And so it would be hard to know their concentration if you just measured right here, because it might have a component of this in there. And so if that's the case, then it might be better to find a spot here that is not influenced by the relative change in this concentration significantly, or maybe this spot here, which is less influenced, so you need a very large concentration to get a small change here, right? So for those reasons, sometimes you will look off peak to get a measurement of a concentration of something. All right, good. Atomic absorption spectroscopy is, again, a form of spectroscopy, and the instrumentation is a little bit different. And what happens is we actually destroy the solution by sucking it up into a nebulizer and then a spray chamber and then exposing it to a flame. Now, have you seen flame tests before on YouTube or in, I don't think we ever performed one in Gen Chem for you. We brought in some lamps that was like that, right? And we showed you all sorts of different colors. But let's see if I can show you a flame test. All right. So this is a flame test here. Well, it's not a flame test.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, and then we have...
So these are different elements. that are burning, and we can listen to what the elements are in a second here. But the point of this is that different elements give off different colors when they are energized by heat from a flame. All right, so the same principle is used. Now here again, this is an emission technique because you are trying to identify what color is emitted, right? Because that color of emission will be related to the different elements. So let's listen to the elements.
Some barium chloride with barium ions burning a yellow, a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
Have you ever seen shooting stars that are different colors, right?
Yeah, once I saw one. It was green.
Yeah, that's right. As we put more and more space material up into our atmosphere, more and more of it will eventually fall down, and we'll see more and more of these shooting stars, they look like, but they're really material burning up as it comes back into the atmosphere. Very high speeds, and then all of a sudden it hits a very relatively, thick layer of material. Before in space, there's nothing, so it's just zooming towards Earth, but then it hits a bunch of oxygen, and the high speeds and the high friction result in high temperatures, which will basically burn up, vaporize the material. But that green that you'll be seeing generally will relate to the copper that is in the space material. Okay, so in atomic absorption spectroscopy, which is a model nowadays, it used to be something that was used frequently, but now it's more of a model, and people have moved on to the same technology, same technique, same principle, but instead of burning it in a flame, in the way you would burn something on a campfire to get light, now we contain the material in a tube, like in light bulbs, right? The tubes that are light bulbs, they contain mercury inside there, like a neon light contains neon inside. You can have a tube that's open, and then gradually pump in the capillary tube here, gradually pumps in your solution, and the metal ions that are in solution, or any atoms, will result in the characteristic spectra, characteristic emission color of those specific elements. All right. So so for a flame, you would use something usually like acetylene, and you generally would use air, but sometimes you would have to use nitric oxide. But again, this is an older technique, and people don't generally use this anymore. They've replaced it with what I was describing, which is called ICP. So in an atomic atomic absorption spectrometer, one of the kind of limiting components, and this is why people have moved to ICP, which stands inductively coupled plasma, all right, which essentially, that's what you have when you have a neon light or one of your incandescent light bulbs, is a plasma inside there, a relatively low pressure, molecules in the gaseous phase, right? Okay, so this is one of the drawbacks to atomic absorption spectroscopy, is the bulbs have to be particular to the elements, because the bulb actually shines a wavelength of light of that element, right? Emits a wavelength of light particular to that element, and then the flame interferes with that particular wavelength, and the degree of interference gives you your signal. All right. So again, kind of an older method, and so I think that's all we're going to do to talk about atomic absorption spectroscopy.